Hi, welcome back. In this video, we're going to do a couple of examples. The first one, we're going to use implicit differentiation to get a differentiation formula or rule for the arc cosine function. And then in the second example, we're just going to use that rule to get the derivative of another function. So the first problem says use implicit differentiation on the equation cosine of y equals x to prove this formula for the derivative of arc cosine of x. So if y is equal to arc cosine of x, then we know cosine of y is equal to x, and so we can use implicit differentiation on that equation to get a formula for dy dx. So let's start with cosine of y equals x. Differentiating both sides, notice we've got a function of y on the left side. That's a composite. We've got an outside function, the cosine function, and we've got an inside function, y. So y is a function of x. So we've got an outside and an inside. We're going to use the chain rule on the left side of the equation. So the derivative of the outside is just going to be negative sine of y. It's the derivative of the outside with respect to the inside. And then we're going to multiply that by the derivative of the inside. And we're just going to write it as dy dx because we don't know the derivative of the arc cosine function. That's what we're trying to find. And then on the right side, the derivative of x is just 1. So now we can divide both sides by negative sine y to get dy dx is negative 1 over sine of y. And the equation, the initial equation told us that y was arc cosine of x, so we write it as the denominator is just sine of the arc cosine of x. But we'd like to get this simplified. So we're going to use the right triangle. Now remember, arc cosine of x means the angle whose cosine is x. So let's label one of the acute angles arc cosine of x. Now remember, arc cosine of x is the angle whose cosine is x, so I can label the adjacent side x and the hypotenuse 1 because the cosine of this angle is adjacent over hypotenuse, which is x. Now using the Pythagorean theorem, we can get the third side of that right triangle. It's the square root of 1 minus x squared. And this allows us to write down the sine of that angle. So the sine of the arc cosine of x is opposite over hypotenuse, so it's going to be square root of 1 minus x squared over 1. All right, so then we can go back to our derivative and we can say the derivative is negative 1 over the square root of 1 minus x squared. That's the derivative that we were looking for. The derivative of the arc cosine of x. All right, let's use that on the next problem. On this one, we're asked to find the derivative of the function g of x equals the arc cosine of the square root of x, and then we have to simplify our answer. So in this one, we don't have to use implicit differentiation because we know the derivative of the arc cosine, but we do have to use the chain rule because we have a composite. We have the outside function is the arc cosine function, and the inside function is our friend, the square root of x. And we know how to differentiate that by now. So we're going to use a chain rule. The derivative of the outside with respect to the inside, so the inside was the square root of x, so that doesn't change, times the derivative of the inside, which is 1 over 2 times the square root of x. That's it. But now we have to simplify our answer. So multiplying the numerators, we get negative 1. Multiplying the denominators, I have 2 times the square root of x times the square root of 1 minus x. So I just, inside the radical, the second radical, I squared the square root of x and got x. So now I can multiply, I can combine those two radicals into a single radical. So it's negative 1 over 2 times the square root of x times 1 minus x. And there's our derivative. All we used was the chain rule and our knowledge of the derivative of the arc cosine function and the derivative of the square root function. All right? We'll do more problems like this using the chain rule. We'll do more implicit differentiation, and we're adding all of that to our toolbox. So I'll see you there.